Mars is the fourth planet from the Sun and the outermost of the four rocky worlds, and of all the planets the most like our own. It is a cold, dry, dusty desert wrapped in a thin skin of carbon dioxide air, and yet it is uncannily familiar. It circles the Sun a little more than half again as far out as the Earth, taking about 687 Earth days, very nearly 2 of our years, to complete an orbit. But the resemblances are what strike one first. A Martian day is only a little longer than ours, some 24.5 hours, so close that the scientists who run the rovers keep their own clocks on it. And its axis is tilted about 25 degrees, almost exactly the Earth's own tilt, so that Mars has the same 4 seasons we do, though each on that longer year lasts nearly twice as long. It is this Earth-likeness, more than anything, that has made Mars the great destination of our exploration. For all that familiarity, Mars is a small world, about half the Earth's radius and barely a tenth its mass, so that a person would weigh little more than a third of their Earth weight standing on its surface. It is also, tellingly, the least dense of the rocky planets, a hint that its iron core is proportionally smaller and lighter than the Earth's, and it is bitterly cold. The average surface temperature is around 60 degrees below zero. Here lies a crucial clue. If one calculates the temperature Mars ought to have from sunlight alone, with no atmosphere at all, the answer comes out almost exactly the frigid figure we measure, which tells us that Mars's thin air traps only a few degrees of warmth today, nothing remotely like the furnace-making blanket of Venus, and that in turn poses the central puzzle of the planet, for its ancient surface is covered with the unmistakable marks of running water, which the cold, thin air of today could never sustain. Something has changed profoundly since Mars was young. Seen whole, the face of Mars is split in two. The southern hemisphere is ancient, rugged highland, standing kilometers high and pockmarked with the craters of 4 billion years of bombardment. Much of the northern hemisphere, by contrast, is a smooth, low-lying plain, sparsely cratered and therefore far younger at its surface. This global dichotomy, old rough highlands over half the world, young smooth lowlands over the other, is one of the planet's deepest mysteries, and its cause is still argued over. Perhaps a single colossal impact gouged out the northern basin, or perhaps some slow churning of the mantle within drove the two hemispheres apart. Beneath it all lies a crust averaging some 50 kilometers thick, considerably thicker than the Earth's, and thicker still beneath the southern highlands than the northern plains. The dichotomy is the canvas on which the rest of Martian geology is painted, and no account of the planet's history is complete without explaining why its two halves are so profoundly unilike. Dominating one whole hemisphere is Tharsis, a continent-sized volcanic bulge some 5,000 kilometers across, covering a quarter of the planet and rising several kilometers above its surroundings, plausibly the region of thickest crust anywhere in the solar system. Tharsis bears 3 giant, shield volcanoes in a row, and off its flank stands the greatest of all, Olympus Mons, the tallest volcano in the solar system, rising some 22 kilometers above the plains, nearly 3 times the height of Everest, and spreading across a base the size of a whole country. Such mountains could grow so vast for 2 reasons the Earth denies its own volcanoes. Mars has no drifting plates, so a volcano sits fixed over its source of molten rock for billions of years, piling eruption upon eruption in one place instead of being carried off as a chain of lesser peaks. And the weaker gravity lets a mountain tower higher before its own weight cracks the crust beneath it. On Mars, the fires burned in one spot, and the mountains grew without limit. The immense weight of Tharsis pressing on the crust cracked it for thousands of kilometers around, and the grandest of those cracks is Valles Marineris, a system of canyons running eastward for more than 4,000 kilometers, a fifth of the way around the planet in places 200 kilometers wide and 7 deep, beside which the Grand Canyon is a mere scratch. It is not a river's work but a great tear in the crust, a rift widened by collapse and landslide. Elsewhere the planet bears the scars of ancient impacts none greater than Hellas, a basin 2,300 kilometers wide and the lowest point on Mars. And over everything lies the dust that gives the planet its color. The famous red is simply rust, iron in the basaltic rock, oxidized over the ages, blown into vast dune fields and blanketing the world. From orbit, spectrometers have read the chemistry of the surface directly, mapping the clays and the salts and the iron oxides, and so tracing, mineral by mineral, the changing story of Martian water through time. For most of the space age, the inside of Mars was a matter of inference, guessed at from its mass and its wobble. That changed in 2018, when a NASA lander set down the first seismometer ever placed on another planet, and listened for the better part of 4 years to the faint trembling of Mars quarks before the dust finally smothered its solar panels. Seismic waves read a planet's interior as a scan reads a body. A quake sends waves rippling through the depths, and the way they bend and echo off the boundaries within betrays what lies at each level. By catching the waves reflected off the boundary of the core, the mission measured for the first time on any planet beyond the Earth the size of a planetary core. Mars's is molten iron, about 1,800 kilometers across, more than half the planet's radius, proportionally far larger than the Earth's, and surprisingly light, which means it must be laced with a good fraction of lighter elements such as sulfur. That its waves carry no shear confirms it is liquid, and a core so large leaves the rocky mantle above it a single shell, for Mars is too small to reach the crushing pressures that give the Earth its layered depths. The same listening revealed the shallower structure. Beneath the lander, the crust proved a few tens of kilometers thick and layered, and the mantle was traced down some 1,500 kilometers, resting on a thick, cold, rigid outer shell. And the reading is not finished even now. Since the mission ended, its records have been re-examined again and again, and in the most recent work seismologists have reported the faint signature of a solid inner core at the very center, a frozen heart within the molten one, much as the Earth possesses, inferred from the deepest waves that pass clean through the planet's middle. If it holds up, it would make Mars only the second world known to have such an inner core, with consequences for how its early magnetic field was born and how it died. That the story is still being rewritten, years after the instrument fell silent, is a mark of how precious that single seismometer's harvest was. It turned the inside of a planet from a guess into a measurement. Mars today has no global magnetic field, but it once did, and the loss of it changed everything. When an orbiter first mapped the planet's magnetism, it found no field radiating from the core, but something remarkable frozen into the oldest rocks, broad bands of magnetism in the ancient southern highlands, neighboring strips magnetized in opposite directions, uncannily like the magnetic stripes that record the spreading of the seafloor on Earth. Those frozen fields tell us that early in Martian history, a churning molten core generated a magnetic field of its own, which the oldest crust recorded as it cooled, and that this dynamo then shut down, more than 4 billion years ago, for the youngest great volcanoes and impact basins bear no such magnetism. Why the core's engine stopped, we do not know for certain, but the consequence was momentous. Once the magnetic shield was gone, the solar wind had free reach to the top of the atmosphere, and it began, patiently, to strip that atmosphere away. Mars is also a world whose very tilt is unstable. The Earth's large moon holds our axis steady, wobbling it by scarcely a degree over millions of years, but Mars has only 2 tiny moons, too small to anchor it, and so its tilt wanders chaotically, swinging over the ages between nearly upright and steeply canted, from almost nothing to as much as 60 degrees. These are Mars's ice ages, and they are far more violent than the Earth's gentle cycles. When the tilt runs high, the poles are bathed in summer sun, their ice driven off and redistributed toward the equator, where glaciers and ice-rich ground form at latitudes that could never hold ice today. When the tilt runs low, the ice retreats to the poles once more. The fine layering of the polar caps is read as a calendar of these swings, and the ghostly glaciers found buried at the mid-latitudes are the fossils of past high-tilt ice ages, for the planet's axis stands, at present, near the low end of its long, restless range. The air of Mars is thin almost beyond imagining. At the surface, barely 0.6% of the pressure we breathe, so tenuous that standing on Mars would be, to the lungs, very like standing in the vacuum of near space. It is almost all carbon dioxide, with a little nitrogen and argon. And because that carbon dioxide is the main gas, and because each pole grows cold enough in winter to freeze it solid, Mars does something no other planet does. It breathes. Every winter, as much as a quarter of the entire atmosphere freezes out of the sky onto the winter pole as a cap of dry ice frost, and every spring it turns back to gas, so that the whole planet's air pressure rises and falls with the seasons. One further consequence of that thin air is stark. Liquid water cannot survive on the surface, for the pressure is so low that water there can only be ice or vapor, boiling and freezing at once, never flowing free. Thin as it is, the Martian air still makes weather. Wispy clouds of water ice and carbon dioxide ice drift across the sky. Dust devils taller than buildings wander the plains, now and then sweeping a rover's solar panels clean. And the winds blow, but the signature of Martian weather is dust. Local storms are common, and every few years a regional storm can swell until it wraps the entire planet, veiling the whole world in suspended dust for weeks or months together. The Great Global Storm of 2018 grew so dark that it starved the solar-powered Opportunity rover of light and ended its long life. These storms rise most fiercely when Mars is nearest the Sun, and the southern summer is at its hottest, lifting dust high into the air, warming the upper atmosphere, and chilling the shadowed ground below. It is a restless, dusty, driven climate, and one lived out beneath a sky with no magnetic shield to guard it from the Sun, which brings us to the deepest question of all: where did Mars's ancient air and water go? The surface testifies that the early planet was warm and wet, wrapped in a far thicker atmosphere, and that atmosphere is now almost entirely gone. To find out where, NASA sent an orbiter called MAVEN, built for the single purpose of measuring how Mars loses its air to space, and flying there since 2014. It found first that the loss is not finished. Mars is still bleeding its atmosphere into space today, a couple of kilograms of gas every second, and it charted the several ways the loss happens, the lightest gases simply drifting off the top, sunlight breaking molecules apart and flinging the fragments away, and above all the solar wind sweeping unopposed where a magnetic field would once have turned it aside, tearing away the electrically charged atoms of the upper air and knocking others loose. Stripped of its shield, Mars lay open to the Sun, and the Sun over the ages carried its sky away. The most elegant proof of that long theft is written in isotopes. When a gas escapes to space, its lighter atoms slip away a little more easily than its heavier ones, so the gas left behind grows steadily enriched in the heavier kind, and by measuring exactly that enrichment, one can weigh how much has been lost. From the balance of two forms of argon in the Martian air, MAVEN scientists reckoned that about 2/3 of all the argon Mars ever had has escaped to space, and scaling that up they concluded that the majority of the planet's original atmosphere is simply gone. The same fingerprint appears in the planet's water. Its heavy hydrogen is enriched some 5 or 6 times over the Earth's, the mark of an ocean's worth of ordinary water broken apart and lost across billions of years. The verdict is that escape to space, more than any burying of the gas in rock, was the chief agent that turned a once temperate planet into the frozen desert of today, though just how much air Mars began with remains an open and much-argued question. That vanished water left its history carved across the surface, and geologists read it in 3 great chapters, dated by counting craters. The more craters a land bears, the older it must be. The oldest chapter, the Nokian, was Mars's wet age. Its ancient highlands are laced with branching valley networks that look for all the world like river systems fed by rain or melting snow, and they hold clays that form only where rock sits long in contact with water, and the basins of vanished lakes with inlets and outlets. Early Mars plainly had a water cycle, standing seas, and a climate warm enough, at least from time to time, to keep water liquid under a much thicker sky. The middle chapter, the Hesperian, was a drying, souring age of catastrophe, not gentle river valleys now, but colossal outflow channels gouged in days by sudden floods bursting from underground, and rocks full of the salts left by evaporating water. And the last chapter, the Amazonian, which runs to the present, is the age of ice and rust, the surface frozen, the water locked away, the red dust slowly gathering. 2 rovers have gone to read that history at first hand. Curiosity, roving the floor of Gale Crater since 2012, drilled into a thick stack of ancient mudstones and proved that the crater once held a long-lived lake, with liquid water of gentle chemistry, the right elements, and the energy gradients that life could feed upon, a genuinely habitable place 3.5 billion years ago. And Perseverance was sent in 2021 to Jezero Crater precisely because pictures from orbit showed there the unmistakable fan of an ancient river delta spilling into a former lake. On the ground, the rover confirmed it. Jezero had held a river and a lake, and the river stopped flowing around 3,800 million years ago at the very close of the wet Nokian age. Where all that water finally went lost to space, frozen into the ground and the poles, or hidden as liquid deep below, is the question that drives everything else. Each pole of Mars wears a cap of ice, but they are stranger and more layered than the simple white hoods they resemble from afar. Over each pole, winter lays down a seasonal frost of frozen carbon dioxide, the dry ice that drives the planet's breathing, which burns off again each spring. Beneath that seasonal veil lie the permanent caps, and beneath those, kilometers-thick stacks of dust-laden water ice, finely layered like the pages of a book, each layer a record of the planet's shifting climate much as an ice core on Earth preserves our own. The 2 caps are not alike. The northern one, once its winter frost has gone, is bare water ice, while the southern keeps a thin lid of frozen carbon dioxide all year round, and radar beamed down from orbit has learned to see clean through these deposits, mapping their hidden layers and their flaws, and even finding great buried stores of frozen carbon dioxide that, were they released, would measurably thicken the planet's thin air. That same radar produced the planet's most contested discovery. In 2018, a bright reflection deep beneath the southern cap was read by some as the echo of a buried lake of cold, salty brine liquid water hidden under the ice. But the claim remains sharply disputed, for the same signal can be produced by certain clays or salty ices with no liquid at all, and the fierce cold at the base of the cap makes stable water hard to credit. It is a result that must for now be held as unproven. What is beyond doubt is the ice buried elsewhere. Vast quantities of water ice lie frozen into the ground across the middle and high latitudes. Buried glaciers, ice-rich soils, whole fossil ice sheets left from past ice ages, some of it surprisingly shallow. This near-surface ice, far more than the distant poles, is the water any future human landing would reach for to drink, to breathe, and split apart to burn as rocket fuel. Yet all the ice we know of, poles and ground together, adds up to far less water than once flowed across the young planet, and where the rest went is among the great unsolved problems of Mars. Was Mars ever a home for life? For the ancient, wet Mars, the case is now strong that it could have been. Curiosity's lake had everything life is thought to need: liquid water, the essential elements, and a source of energy, and both rovers have found organic molecules in the rock. But organic carbon is not itself a sign of life, for it can be made without life and delivered by meteorites, and the true test must wait for Martian samples to be studied in laboratories on Earth. For the surface of Mars today, the verdict is harsh. Liquid water cannot last there. The soil is laced with toxic salts called perchlorates that, under the planet's harsh ultraviolet glare, turn actively lethal to microbes, and the ground is scoured by radiation. If life survives on Mars at all, it can only be underground, a few meters down, shielded from the radiation and the ultraviolet, perhaps in reach of buried ice, and no trace of it has yet been found. That radiation is the gravest hazard facing any human who would go there. With no magnetic field and next to no air, the surface of Mars lies open to the cosmic rays that stream through the galaxy and to the particle storms of the Sun. Curiosity's radiation detector measured a steady dose on the ground and a heavier one still during the long voyage between the worlds, enough over a round trip to raise a traveler's lifetime risk of cancer meaningfully and to weigh heavily on the design of any crewed mission. And there is one last, tantalizing possibility deep down. A recent study, rereading the seismic data, argued that a fractured layer of the crust, some 10 or 20 kilometers below the surface, might be soaked with liquid water, enough if it spans the globe to fill a shallow planet-wide sea. It is a provocative idea and a disputed one, for others have shown the same data can be explained by a bone-dry crust. But if such a hidden reservoir is real, it would be, far below the reach of any drill we now possess, perhaps the most promising place in the solar system to search for life beyond the Earth. No world beyond the Earth has been explored as intensively as Mars, which now, for the first time in history, hosts a permanent robotic presence tended by many nations at once. 2 nuclear-powered rovers roam its surface: Curiosity, still climbing its mountain of layered rock, and Perseverance, which in Jezero has been drilling and sealing samples of rock and soil. More than 30 tubes so far, to be cached against the day a future mission can carry them home, the long-cherished goal of Mars sample return. Perseverance even brought a tiny helicopter, Ingenuity, the first machine ever to fly under its own power on another world, which made 72 flights before it was at last grounded. Overhead, a fleet of orbiters circles American, European, Indian, Emirati, and Chinese, mapping the surface in exquisite detail, sniffing the atmosphere and relaying the rover's findings home. Mars has become a crowded frontier, watched and sampled and mapped, its every dune and channel catalogued from above and below. 2 small, dark, potato-shaped moons complete the Martian system: Phobos and Deimos, perhaps captured asteroids, perhaps debris flung up by some ancient impact, their very origin unsettled. The inner one, Phobos, races so close above the surface that it circles the planet faster than Mars itself turns, rising in the west and setting in the east, and the tides are dragging it slowly downward, so that in some tens of millions of years it will either be torn apart into a fleeting ring or crash into the planet below. In the end, Mars stands as the great object of our outward yearning, the one other world near enough, and enough like our own that we have turned it from a wandering red point of light into a mapped and measured place, walked by our machines and perhaps one day by ourselves. It was warm and wet when the earth was young, and something took its air and its water away. And to read that story in full is to learn not only the fate of one planet, but how narrow and how precious is the margin that keeps a world alive.